Thanks so much. Thanks so much for the kind introduction. As already mentioned, my name is Filip Nikolic. I currently work at Isovalent, the creators of eBPF and Cilium, which is now part of Cisco. So in today's talk, what I want to go about is not focus on just one specific CNI, as you may think of it. Rather, I want to take us a step back. I want to show you something that applies to every single CNI that's out there. I want to show you exactly what a CNI actually does and that there is no black magic being involved. It's just a logical step that we're going to go through, and by the end of this, you will have all the knowledge necessary if you wanted to go home and implement this by yourself. So let me start first by obviously explaining what is CNI. All right, what is CNI? CNI stands for Container Network Interface. You can see two logos being here, and oftentimes when we talk about CNI, you think about something like Cilium, right? But as actually, if we are pedantic about the word CNI, Cilium is not a CNI by itself. It actually is rather an implementation of things, all right? On the left-hand side, we can actually see the CNI project itself. The CNI project is a CNCF project on its own. It's currently in the incubating status of the CNCF landscape, and it basically defines the intersection between a container runtime and the so-called CNI plugin, which is the implementation of a CNI. If it didn't confuse you enough so far, we'll get to it in a bit. So here is what CNI is. This is the repository I wanted to mention. It is a repository on its own, and essentially it's just describing what a CNI exactly is, but the important aspect here is that there is a specification. And that specification, you can think of it similar as to a protocol. It is just defining what a CNI is actually supposed to do. That's pretty much it. So if we now take this example here, a user wants to submit some kind of a pod YAML, right? Sends it over to a Kube API server and wants to launch the best app ever, right? The Kube API server then will figure out through internal Kubernetes things, through the scheduler and whatnot, which node this pod shall be scheduled on. So after some time, it will know which node this pod is supposed to run on, and it will contact the kubelet on that node. The kubelet is just a running agent that runs on each and every node in the cluster, regardless of it being a worker or a control plane node. And so the kubelet actually does not create those containers for you then. It is basically just there handing on and managing these things and passing it on further. So what it is doing is the kubelet will then invoke something called the CRI, which is responsible for container management. And the CRI will then take the job of creating that specific container. Once that is done, the CNI comes into place. So the CRI is going to invoke the CNI, and now it's the CNI's job to configure the networking of that specific container. However, that's actually not quite correct. It's not so much that it's the CNI that does it, it's the CNI plugin. It's just a semantical difference, but an important one, as we'll see. Oftentimes in the community, we just went the wrong way, and we like abbreviations so much, so we're just using them, even though we shouldn't really. What actually the CNI is it's that path in between. It's the path between the CRI and the CNI plugin. It's just specifying the communication aspect of it. So it's defining an API and what you need to adhere to. However, for simplicity reasons, the community started to use the word CNI for the actual implementation of things. But as mentioned, it's not entirely correct. So now, what about the goal? The goal for this presentation is the following. We are going to write our own implementation of a CNI from scratch, having nothing else available to us. And what we're going to do exactly is the CRI is going to provide a so-called network namespace for us. Now, in case you're not familiar with network namespaces, in essence, they are Linux technology. They don't have anything to do in common with Kubernetes namespaces, in case that sounds familiar to you. Totally two different things. Network namespaces basically mean there is some kind of isolation. The kernel speaks of isolations when describing namespaces. What it means is whatever kind of network configuration you're doing within, that specific namespace is staying within that specific namespace. So you can have multiple network namespaces, you can go ahead and configure them differently, and it will not disturb the other ones. So you could go ahead and have routing tables in there, you could configure interfaces in one, and it won't change the actual configuration of other network namespaces. And the CRI is responsible for creating such network namespaces. This is what we refer to in the Kubernetes space as a pod sandbox. So whenever you create a pod, the CRI is actually going to create two containers for you. The first one being this pod sandbox, which is important for us for the network namespace, and then your actual container. But we won't go into much more details about the CRI. If you're interested in this, I actually have an entire repository where there is one written from scratch that you could look at with some code comments in there. It's going to have some further explanations down the road as well. Anyhow, so what we are going to do, though, is once CRI creates such a network namespace, it's going to invoke our CNI that we're going to write. And that CNI is now going to put interfaces in there and configure them correctly. And this is exactly what we are going to do. So to summarize as well, CNI plugin, what is it? Summary. So CNI is the API between the container runtime and the CNI plugin, and it is a CNCF project on its own. You can find it on GitHub under container networking/CNI, and the plugin is the actual software responsible for the configuration. And it receives its tasks from Kubelet, and it is an implementation of the CNI spec. So let's go through it step by step to exactly know what we now need to do in order to have our own CNI. So what we need to do here is the following. We'll just zoom in to the communication aspect between CRI and CNI. As mentioned, the network namespace is not being created by us. That's something that the CRI handled for us. So we can have it as a given. Now, the very first thing that the CRI is going to do is it's going to look in a certain path. That path, by default, is /etc/cni/net.d. And in there, it will now go ahead and look for the very first file that it can find. This is as well why inside of that directory, you usually see some kind of a prefix. And that prefix will usually contain a number, such as 10 minus something or 50 minus something, so that it gets hopefully listed as the first file in that directory, because that's the one that the CRI is going to read. So after reading that, it's a simple JSON. JSON structure is very simple. We'll simply define their CNI version. There's different kind of specs, different kind of versions of the CNI spec, and then you can give it a name. The name can be pretty much arbitrary. Here, we decided on from scratch. And then as well, we'll define a type. And you can see that I highlighted this type because that's the important key aspect here. The type, when we set this to demystifying, what it means is that in the next step, the CRI will now take that demystifying and look in another folder that's very important. It now searches for an executable in /opt/CNI/bin. And it is looking there for an executable called demystifying. As we previously told it, that's going to be the type. And please make sure that you understand what I mean by executable. Oftentimes, we have this convention, everything related to Kubernetes, everything related to containers nowadays needs to be written in Go. That's actually not the case at all. It just needs to be an executable, whatever that is. If you wanted to, you could make it Python, you could make it Rust, you could make it in C, you could do it however you want. And as a matter of fact, since not everybody here usually writes code and likes seeing code snippets, we're actually going to do this entirely in Bash. So, how exactly are we going to do this? The CRI is now going to invoke our executable, and it's going to pass certain environment variables to us, right? The environment variables you can see here, for example, there is CNI_command, which is set to add, CNI_netns, which stands for network namespace, and CNI_ifname, which stands for interface name. There's a bunch of others that just for simplicity reasons I didn't put on here, and there's further information that can be passed via stdn, but it's not really too important for our use case here. We'll get to the specifics of these environment variables in the following slides. So the very first thing that we need to do is we need to create a virtual Ethernet pair. Now, for those of you unfamiliar with what exactly that is, it's quite simple. It's just a special kind of interface, and they always come in pairs. So whenever you want to create a virtual Ethernet, you will actually create 2 instances of them. And the idea is simple. Whenever you send packets over one of those interfaces, the kernel will automatically send them to the other end. So far, so simple, right? It may actually sound very useless at first, like why would I want to do this? Why do I have these 2 interfaces? I send something on the one thing and it's being sent to the other. We'll see in a second why that is. But first of all, we need to understand how can we create this. And there's a very simple command that we can use for this. You'll see a lot of times we'll now use the IP command, because with the IP command, we can actually go ahead and do a lot of network configuration aspects. So in our particular case, we're going to use the IP link add command. And you can see there that I then specify one of the names of those interfaces. In our case, I named it vth_host. Then I'm defining the type, which is a vth. And now I need to define a peer name, because remember, they always come in pairs. And so by doing this, we're basically now creating 2 interfaces that are interconnected with each other. So we have now on the host system, this is running on the host system, we now have the vth host and we have the vth netns interface. So what happens next? Now we want to move one of these inside of that network namespace that we talked about earlier, right? Remember, the namespace is just some sort of isolation that allows you to put stuff in there and do network configuration without it affecting other things outside of that namespace. And so we now want to put one of those in there. How do we do this again? Well, IP command to the rescue. So we'll just IP link set the virtual Ethernet netns, and then we'll go ahead and specify which netns, which network namespace we want to move those in. And you can see this highlighted here. There it says then something like CNI -7B whatever. Where exactly does this value come from? This is what we have from one of the environment variables that were passed to us when the executable was triggered. If you remember, we have this environment variable called CNI_netns, and so we're simply parsing that, and by that we now have the name of the network namespace, because we need to be able to distinguish between them, right? Every pod will have its own dedicated network namespace, and so we need to assign unique names to them in order to know in which one we now want to operate. So what we're going to do here is we're simply sending that or putting that interface in there. Now, what's next? Well, obviously, we need some kind of IP address, right? So we're going to assign an IP address inside of the network namespace for that specific interface. This is what's known as the pod IP address. So when we do this here, we will again leverage the IP command for this. We'll simply tell it IP -n, again specifying the network namespace that we want to perform configuration in, and then we'll say add the address 2.244.0.20, right? And then go ahead and assign it to the device, to the interface called vth_netns. So far, so simple. So what's next? Obviously, we want to do the same thing as well for the other one. We're going to assign an IP address for the one that's remaining on the host. Remember, the one called _host is running on the host system, so in the host network. The other one is running in the pod network namespace. So we're assigning here another IP address as well. We can choose whatever we want to. We did it here with 0.101. Now, the next part is that we want to rename things, right? If you ever looked inside of a container and you did an IPA and listed all the available interfaces, you will actually see that they are usually always called the same way, and you wouldn't have some kind of overlaps there, right? And so you would as well have a very convenient name that people are usually knowing already, which in our case is Ethernet 0. Where exactly does this come from? Well, we have another environment variable that the CRI passed to us, where it simply said, hey, this is my preferred name for the actual interface that you're supposed to create within the container. So please name it Ethernet 0. How do we do this again? IP command to the rescue, IP minus n. We know about this part already, right? Specify the network namespace because we're operating in there. And then we're saying link set for the veth_netns, which was the previous name, and now rename it to Ethernet 0. So what's next? What's next is that we somehow need to be able to properly have traffic coming from one end to the other, and knowing how to send it there, knowing how to reach perhaps the internet, knowing how to reach other applications on that node, and so on. Now, for those of you that aren't really familiar with networking, it's quite simple, but the really important aspect that we now need to talk about are routing tables. So what are routing tables? Routing tables are essentially a way how you can tell your operating system what to do with a certain packet given a certain destination, right? Whenever you send off a packet, you will usually have some kind of destination IP, which may be 10.10.10.10, and you will then have to say, hey, please send this over this specific interface. What we'll have to do on the host side is the following. We'll have to configure a routing entry where we say for destinations 10.244.0.20, please go ahead and send this over the interface veth_host. Now, why do we have to do this? Remember, the IP address that we're actually putting in here is the IP address of the pod, of the network namespace that we have there, right? What we want to do is for the system to know that whenever there is a packet designated for that specific pod, it's supposed to send it to the interface which is residing on the host. And this is where virtual Ethernet pairs come in handy, because as we mentioned, whenever you send something to one end of a virtual Ethernet pair, the kernel is going to forward it to the other side, right? And this is how packets can traverse from one namespace to the other. And so we now have to do this on the host system. So how do we do this again? IP route to the rescue. So IP route add, and we're simply adding the route for the destination 10.244.0.20/32, and we want this to be sent over the device veth_host, right? By that, we now made sure that whenever there's packets for that, they're gonna travel to the network's namespace. But now the problem still is, how does traffic now come out of the network namespace? Because remember, everything that we do on one side doesn't affect other things in another network namespace. So obviously, we'll still have to do some configuration over there as well. The way how we're going to do this is by adding some routing entries in there as well to that specific table. Remember, network namespace means isolation, meaning we need to do this for each and every namespace. It's not applied universally. There's two things now that we need to do here for the pod itself. So first of all, very simple, we're as well going to tell it when you want to send traffic to 10.244.0.101, you will have to send this, please, over the device Ethernet 0. Why? What does this accomplish again? It means that kernel will forward it down to the other interface, which means it is then on the host, right? But now the question is, what if we do not want to contact that specific IP address? What if we want to communicate to the internet? There's some other kind of IP address. What if we wanted to perform some kind of DNS lookup over 1.1.1.1? Well, in order to do this now, we will have to specify a certain gateway. So we'll be in there and we'll specify a so-called default route, which basically means if there is nothing that is more specific, use this entry, which is the entry at the very top that you can see. So we're saying default via, which just means anything that otherwise we didn't specify, please send it over 10.244.0.101. And then the next entry comes into place, because now the kernel knows, oh, I need to send my traffic to 101. So it is checking the next entry where it specifies, oh, 101, which interface is that? And it's going to find that the interface is Ethernet 0, send it over, and we successfully now have traffic launching between the pod and the system itself. after we did all of this, we somehow need to communicate back to the CRI what exactly it is that we did, right? It now wants to know some kind of status, it wants to know what we did, the interface we created, the IP address, and so on. And in order to do this, the CNI is now writing a JSON into standard output. So just std out that we need to write a JSON back to. The JSON contains some information like CNI version, the interfaces, the MAC address, and so on of the specific interface. We'll get to that in a bit. Now, in terms of the results, we now have all the necessary steps that we need in order to create our own CNI, and now this is usually the part where people do a demo, right? Unfortunately, as many people have seen at conferences always, things go wrong at demos, right? And instead of me doing 50 typos, admittedly, it will be more hilarious of a presentation than the current one. However, it just doesn't really give you as much of a thing in terms of what it actually is. So I'm just going to put the snippets up here, and you will see how things are going to work. So the first thing that we need to do, as we mentioned, is in the specific folder /etc/cni/net.d, we need to create a JSON file. We put in there whatever's necessary, and the type needs to be the name of the next file. So for the next file, we're creating it in /opt/cni/demystifying. And now this is exactly the bash script that I talked about, right? We have there a shebang at the very top. We'll have to set the modifier with a +x in order to make it an executable. And then we'll just go through the steps that we went through. So first of all, we create a virtual Ethernet pair, right? Then we put one of those interfaces inside of the new network namespace that was created. Then we assign an IP address to that specific interface. Then we're going to assign an IP address to the other one. Then we're going to rename it. Then we need to make sure that everything is up and running. Just a simple command for this, where we ensure that all of them are up. And then we add the routes. And that's pretty much it. And now, as for the last part, we obviously have to go ahead and send the JSON back. So we have a JSON in there with some variables as for the name, the MAC, the sandbox, the address, and so on. And so we'll then populate the JSON by figuring out what the exact MAC address is, by figuring out what the exact IP address is, and we'll just do, at the very last line, a print where we print that back to standard output for CRI to have that. And that's exactly how we're going to create our own CNI. Now, to show you as well, after you've done all of these things on the node itself, you can create a pod. And once you created that pod, once that YAML file has been sent over and everything was created, you will see that container is being created. And sometime afterwards, you'll see that status reports back it's running. And what's important here is this specific IP address, which is exactly the IP address of the interface that was inside of the network namespace. This is exactly what you will see once you do a -o wide. And now we can go ahead and perform a curl from the system itself. We could do it from within the pod as well, and we'll see that it works. Now, all of this is to say as well that this is just a tiny, tiny, tiny piece of what a CNI is actually supposed to do, right? What you can see here is a screenshot of the actual CNI spec. And there's a lot of things to think about. Even this is just a tiny snippet of what we need to do. What we focused on here today is the add operation. So what we did here is we added network configuration to a specific container. Obviously, what would have to happen is as well that we think about the other aspects, such as deleting things, such as how do we check things, how do we do error handling, what's the versioning, and so on. Because that's everything that we need to do. So while you now are capable of writing your own CNI, please do not do it. We all know how that's going to end. So instead, what can you do? Well, luckily, there is actually a graduated CNCF project that does all of this for you. Ta-da, Celium, right? To the rescue. This is exactly what you want to use. So instead of writing your own, although you now could, rather use that knowledge as some kind of debugging tool, some kind of tool that you can use in case you ever face issues. You now know exactly where to look. You now know the paths that are important, and you're able to develop these things and configure these things a bit more efficiently than before. But whenever possible, stick to a well-known CNI that you can trust and use that because it has all of that functionality already battle-proofed and production-ready for you. So to summarize, what does a CNI do? The CNI handles network configuration for the network namespace, which as well we usually refer to in Kubernetes context as a sandbox container. It is not a runtime requirement. As you saw, all we did was during the startup create those things, which means after we've done this, we could entirely remove the CNI if we wanted to. It is not necessary anymore. It's not necessary anymore for any kinds of load balancing. It is not necessary for you to contact the services. All this kind of things, a CNI is not necessary for. There is obviously a couple of exceptions where you could configure it differently, but as a matter of fact, what CNI is defining is that it's not a runtime configuration, and you just need to do the initial configuration while starting and taking it away. And there's two important paths to remember here, /etc, CNI netd, and opt CNI bin. And with that, thanks so much. What you can see here are two links as well, the one being to the demystifying CNI aspect, the CNI that I mentioned, where you'll see some code comments in there, what a CNI is supposed to do, and how to create your own. It's a bit more complex than this talk. It's written in Go, because it's easier for that specific use case. And in the bottom right, you can actually find the repository containing all of this code for you to try out, and it's written in form of a blog post so that actually you can revisit everything that is said here, and it's going to guide you step by step through what you need to do. Thanks so much.
Thanks very much, Filip, for this very interesting insight. Are there questions? We have time for plenty of questions.
Don't make them too hard.
I'm not going to make it hard. Did I get that right, that the example right now just hard codes the IP address, so it works for the first pod only, and then it doesn't work anymore because of IP address conflicts?
Absolutely correct. So what was referred to is here the snippet where we are configuring, the IP address and statically setting it to 10.244.0.101. Obviously, you would want to have some kind of a pool in there. The only reason why I didn't include this in here is, first of all, it's just a simple example. Second of all, it would take another 5 line of bash or very complicated awk setup for people to parse, and it would not look as good on slides. So that's the reason why we're statically setting it here. And again, the pointer to do not just copy this and run it in production, obviously. You will need more than one IP address, otherwise you will not have a lot of working workloads on your cluster. Yeah. Another question behind.
It's less of a question than something when I see this snippet. When you went through what you're doing, in the first time you specified the IP, I think you were using a /24, which is probably, this would be the correct one. And if you go a few slides before.
Few slides before.
Further back. Yeah, I think you don't want to have it on /24.
Oh, yes, I'm sorry, yeah. The script is the correct one, yeah. The script
because
here is the correct one, where it says /32. Yes,
okay.
Indeed.
Thanks a lot.
Thanks so much.
Further question up here.
Oh, man is so weit für.
Don't hit someone? Okay.
Another one. Was it really needed to, could we have the same IP address on both sides of the vEthernet?
To have the same IP address on both sides of the vEthernet?
Yeah.
Again, since those are different network namespaces, you totally could, because the routing table, there is no conflicts in there. Yeah, so you could reuse this. One pattern that you oftentimes see there is that as well, the veth host one will usually reuse the exact same one in order to not take away too many IP addresses. But if you want to, yeah, sure.
And you said we could have multiple CNI files in attendees CNI and not D. How does that work? Which one is selected? Only the first one, or?
Yeah, so only the first one is selected by the CRI, alphabetically speaking, and then you can implement something called chaining if you truly wanted to go further and have multiple CNIs performing some work. So initially, there's some examples in the actual CNI repository where you can see how chaining is working. Essentially, what you're specifying in the JSON output is then, hey, please, after I've finished my work, please go on and call another thing. And this is how you can chain multiple CNIs together. However, there is some issues there because you now need to really make sure that the one does not undo what the other one does. So there's a lot of trust being involved there, which is oftentimes why people prefer to stick to just one CNI instead of having multiple. But to answer your question, yeah, the first one is being chosen.
Thanks.
Can I ask a quick question? Might be what you are asking, but I didn't fully understand. Is on this IP you have 0.20? Let's say on this particular node I have 100 pods. Would this IP 0.20 needs to be unique for each of the 100 pods on that node, so the host knows how to route?
Correct. So the 0.20 is exactly coming back to the question previously, where you would need some kind of pool mechanism and not hard-coded like here. You would then always select a different one and make sure that they do not collide, because otherwise you would now have multiple ones and you would have to choose just which one device you want to send them to. And so one of them essentially will never receive traffic. That's what's going to happen.
Thanks for the clarification.
You're welcome. Another one over there.
So how is it about routing between nodes? Because we didn't talk about that at all.
Yeah, so exactly this specific example was really just one node cluster of things, because obviously it makes things a bit simpler. In essence, what you would see for multi-node clusters is that you would need additional routing information that shows you, hey, if there is this certain IP address that you want to communicate to, which would have the entire CIDR range of that pool, then you would, again, similar like we did here with the default route, you would configure a new gateway. So you would say, for the IP address in the range 10.220.0.0/24, for example, please send all that traffic over the node, and then you specified the IP address of the next node. And so this is then where the other node receives traffic, and then it's going to check the packet again, and it will see in its routing table, it is destined for that specific pod, send it over that, and so on. Yeah. Something as a homework assignment in case somebody wants to go ahead and do this in a multi-node version. Those are essentially the steps to do it. Does that answer your question?
Yes, thank you.
Good.
So before we heard a talk about mutual TLS. Now, if we were to encrypt our traffic, would that be happening on the VF mechanism, or where would you hook in?
Fantastic question. So for the encryption aspect of things, in essence, what you want to do, again, there's different kind of concepts how you could implement this. You could make it part of the CNI, but it doesn't have to be, right? It's not a requirement for an actual CNI. Oftentimes, this is being leveraged by CNI since it's already performing a lot of this configuration aspects. So oftentimes, when you are talking about some kind of encryption method, you're using whatever kind of VPN, what happens is that you create a specific new interface on the host system there, okay? So that host, that interface on the host system is then going to do the encryption once packets go in there. Now, what you need to do over the routing table is just to ensure, again, that when something is destined to go outside of that node, you're going to send it over that specific interface. This in case of lower level encryption. Now, to your particular question about MTLS, for example, this is something that then just happens further up the stack, which means that you would have the applications communicating with each other normally, and they would just exchange certain keys in there. They would have their certificates, you would validate those, and so on. So from a networking perspective, there's then not a lot anymore that you would have to do, unless you're trying to do some kind of perhaps layer 3, layer 4 encryption mechanism where you really are using some kind of VPN, such as WireGuard, and multiple interfaces come into place. So with MTLS, it's not really much to do with the interface itself anymore. You're just sending it to the application, and they are figuring it out themselves.
But if I were encrypting on the CNI, then I wouldn't necessarily need to additionally encrypt.
If you were to encrypt via the CNI by a mechanism such as the interface that I mentioned, then correctly, you wouldn't have to do another sort of encryption. But then you have to think about the following, that this only works for other nodes that do the same thing, right? Which usually means only for the same cluster, because that's where your CNI is running. An advantage that MTLS, for example, still has is that an application running in a Kubernetes cluster could reach out to another application running outside of Kubernetes, and they could share their certificates and key with each other, right, and establish MTLS through regular means as well. This obviously isn't the case if there is no CNI running over there to decrypt the traffic. Does that answer your question?
Yes, thank you.
Amazing. All right, so many questions. Come on, people.
I have a question about your deployment is very simple. You just have this binary in opt, blah, blah. For more complex CNIs, is there also a mechanism where I could have the CNI running inside a container?
Great question. So obviously what I showed you here is the very simplistic version of how to do this by having this executable in there. Now, what you could do if you wanted to, and how more sophisticated CNIs actually work, is they're running as their own container. All right, they're running as their own container. And the plugin is very simplistic. To explain it quickly, what you can think of is it's essentially performing a curl via usually a REST API, performing a curl to that container, and that container is doing the exact same job that we showed here. It's just basically laying it off. So this script would be very simple. Just put a curl in there to your specific container. Your container is going to do the work. Obviously, it now needs sufficient permissions to do this, such as netadmin, in order to do all of that configuration aspect. And that's it. So if you want to, you could have this even running not on the same node if you wanted to. It doesn't really make sense, but you could connect back to it via SSH. So the ways of how to deploy this are up to you. Another question. Oh my God, we're running circles here. I feel like my explanations just lead to more questions as if I'm explaining something very
the
poorly.
Explanations are very good. That is why they are very good questions.
But probably.
So if you run the CNI in a container, how does bootstrapping work? Like if I want to curl the container
Yes.
and it isn't set up yet, how does it work?
You see, there are so many details to these that simply for slide reasons and time reasons, I do not really go into, but since the question was asked. So obviously, there's now a bootstrapping issue since I explained now that you could run your CNI as its own container, right? But now the question is, if you have it running as your own container, for example, a daemon set, how is the CNI being configured if it is a container itself and its configuration, right? And so that's actually the thing. What you will see is that a CNI usually uses a flag called host network, and it's set to true. What this is doing is it is not going to create a network namespace for that container. Okay, that's what the flag host network true is doing. So usually when you create a pod, it is going to create this sandbox, which is important for that network namespace. If you do something with host network true, it is never going to create that pod sandbox. So there will be no network namespace because you'll be really running inside of the network namespace of the host, therefore the name, and hence there is no bootstrapping issue because you're on the system itself. Yeah. All right, somebody else wants to give it a go, or are we done?